Hi, my name's John Harrison. I want to talk to you today about Gaia Engineering and the new TecEco NMG process to sequester massive tonnages of CO2 into the built environment as synthetic carbonate concrete. As of 2011, according to Nature magazine, Peters et al., there are 33 billion tons of carbon dioxide emitted annually to the atmosphere from anthropogenic sources. Portland cement is a major contributor at 8.8%. Geosequestration does not look like it's going to work. Leakage is the problem. I realized that the answer to the world's problems lay in an industrial ecology that utilized waste like CO2 and bitters, desal wastewater or oil process water to create valuable products for the world's biggest market. By including the manufacture of not only TecEco patented carbonating cements but aggregates in the concept of synthetic carbonate building products, a solution to global warming could be found. TecEco have changed the technical paradigm in favour of making CO2 and other waste resources. I started back in about 1999. I was published by Fred Pearce in New Scientist in 2002. There is a way to make our streets as green as the Amazon rainforest. Fred should have referred to concrete. That's the only error in his work way back then, and the major change that we have made. Look at the potential. Over 20 billion tons, if you include aggregate, in our natural geometric process to produce man-made carbonate or synthetic carbonate. If all of concrete is synthetic carbonate, then the sequestration potential is absolutely enormous. You can almost solve the problem just like that. A viable sequestration technology must be simple, scalable, have low upfront capital costs, low environmental impacts, produce saleable product into insatiable markets. Now, this is one area where we are different to all the other solutions. It must be easily implemented and deployable over a wide geographic area. Ideally, it should be symbiotic. It should conform with the rules of a good industrial ecology and address more than one of the major problems facing the planet. Utilize wastes from many sources and produce outputs that can be utilized. Gaia Engineering satisfies all the requirements of the criteria I set out in the previous slide. It can interface with many other product streams and processes, and it produces outputs that can be utilized, all of them, or recycled. It's the lowest cost option with the least environmental impact. The process is scalable and can use intermittent energy from non-fossil fuel sources, and preliminary designs rely more on the scale-up of individual and small decentralized plants. The built environment represents what we do on this planet. It is large, an insatiable market for our product at the right price. Gaia Engineering can address other problems such as waste utilization and producing cleaner water. It achieves the maximum theoretical sequestration from concrete. Our tech kiln and our MG cements have patents or patents pending. It involves no mining, no transport, no grinding, and it does not utilize silicate like the other processes do. It's potentially much cheaper than these old processes like the nettle process. There are no wastes produced that cannot be used or recycled. Not yet being developed, but they should be much, much lower because we don't have all that process. Think for a moment about carbon sinks. Sorry, going back to that. There's no mining, no transport, no grinding. and there's no need to process silicon. That's the point. Think about nature for a moment. The natural sink is carbonate sediment, over 40 billion gigatons. They're permanent. We've got a choice, calcium or magnesium. We've gone for magnesium because of the low molecular weight. It's ideal for scrubbing CO2, and again, because of the low molecular weight, you can sequester more carbon dioxide. It's the 8th most abundant element, and if we run out of waste like desal wastewater or oil process water, we can always use seawater because there's 1.29 grams of magnesium in every litre. Has low pH and polar bonds. Ideal. There are a lot of magnesium minerals. We've chosen nesquihonite. A lot of reasons for that. It can be manufactured in our NMG sub-process at room temperature. There's significant molar volume expansion. Excellent morphology. Photograph long needle-like crystals that add to microstructure, and strength of a composite like concrete's all about microstructure. It can be used directly in acoustic panels, insulation, etc. It can be used as an input source for the manufacture of man-made aggregate. It's stable over a wide PT range. It's suitable for an input to manufacture MgO, our binder. It has low pH and it polar bonds. My colleagues Vincenzo Farini, Silvano Mignardi and Caterino De Vito at the University of Rome, La Sapienza, have developed a process based on some early pre-World War II patents, and also on some recent publications in the 70s by the DOE, or scientists from the DOE. We hope to convert this batch process into a continuous automated process, and we need to plug into, or plan to plug into that, our kiln for making our binders, to recycle the CO2 from the kiln back into the process. We need still to work out what we can do with other salts and how we can make them, what the ideal pHs are and conditions are, etc. A moment about the structure of nesquihonite. It's not like any other carbonate. It can hydrogen bond. There is a big case for manufactured aggregate, whether they be synthetic carbonates or made from fly ash or other wastes. Sand and stone are in short supply in some areas. In the case of nesquihonite, it's an ideal micro aggregate. It's also an ideal starting point for the manufacture of a synthetic carbonate aggregate, using MgO made from it as the binder and perhaps other wastes. MgO has high molar volume growth, ideal microstructure, bonding, stability, and an ideal pH regime. Sequesters CO2, and we already know how to agglomerate fly ash, but we're just keeping that a bit quiet at the moment. This is really a sort of school poster, but it just gives a very graphical representation of the concept. It's a little more interesting. It shows a sort of flow chart pictorially from waste to nesquihonite to cement to the manufactured built environment, and to manufacture building components, aggregates for the same purpose. Other wastes are also. This is the big picture concept. Gaia Engineering. There are a lot of sub-processes that I won't talk about today that we hope to plug in later. The NMG process is what of importance to the present time. Before we move on to that, just a quick talk about thermodynamic cycles. Where we are at now with our eco-cements is that we don't capture CO2. That means basically we have a process energy, so they're not completely carbon negative. They're much lower carbon, but not carbon negative. If we can capture CO2 and put it in, then we have a giant CO2 capture thermodynamic cycle. There are 3 steps to the thermodynamics of that, as in the next diagram. Step 1 is capture of CO2 from industrial processes. to make nesquihonite. Step 2 is the calcination. There are some small process emissions here. And step 3 is the recarbonation of our cements. Again, we absorb the stoichiometric amount. All up, over 1.75 kilograms CO2 per kilogram of our magnesium eco cement. Talking about aggregates, step 1 only, over 1 kilo of CO2 synthetic carbonate aggregate. Very like the solvay process. Happens reasonably quickly, less than 10 minutes. Occurs at an easily achievable pH. The reactions are a bit complex, but you can study this later. We have lots of input plug-in side processes. Kiln is important, and I'll talk about that. It operates in a closed system and therefore does not release CO2 or other volatile substances to the atmosphere. It can be powered by non-fossil fuel sources. Now, the wind's here today, not tomorrow, and so on. We need to learn to adjust industrial processes to use energy when we have it, not necessarily focus just on storing energy. It calcines and grinds at the same time, therefore runs more efficiently, and it produces a highly definable product. We can use the CO2 produced in our NMG process to make the aggregates, as I've explained in the previous slides. There's a reasonably high enthalpy for calcining nesquihonite, but the important points to notice is that much of this is consumed at low temperatures, driving off water, and therefore waste energy can be used. 20 for driving off CO2 and the last water molecule. There's several other outputs from Gaia Engineering it can deliver. Ultimately, there's a route to energy and fuels. There's also a route to fresher water. Sorry, our costings are still under construction. We're working on that, but we expect them to be at least half that of Portland cement, probably less. It's an example of a geomimetric industrial symbiosis. And finally, I'll talk to you about geomimicry. Look at these limestone cliffs. They cover about 8% of the crust. They're the work of shellfish and other species producing carbonate biologically over millions of years. In every litre of seawater, there's 1.2 to 3 grams of magnesium. There's enough in seawater if we run out of waste like desal water and oil process water to last basically forever. To survive, we must mimic these seashells and build our homes using alkali warming problem and balance the carbon cycle. We need to do the same as these big old trees. We need to consume CO2 in the built environment. TecEco today have patents or patents pending. We're in the chasm due to the GFC. There's been not so much interest in solutions. People talk more about the problem than the solutions. Help get us out of here. Please contact us. Show your dollars. We're keen to get on with it. And thank you so much for listening.